Sir, now it is audible?
Yes, sir, it is audible.
Okay, sir. Okay. So sorry for the delay, sir. Yeah. Yeah, dear students, now I'll go with this. So this I have to explain once again. So now we are going to discuss about backtracking. So in the backtracking, so in the backtracking is the one process which is to solve the problem. You can say this backtracking approach will solve some set of problems like dynamic programming. But in the dynamic programming, we followed a sequence of solutions. That is principle of optimality. The sequence of solutions we solved. Among that, which is the best one. In the backtracking also, it uses a brute force technique. So what brute force technique says that we should try to solve all the possible solutions for the given problem, and among the possible solutions we'll select one solution as a desired solution. So that is brute force approach. That brute force approach technique is using in the backtracking. So first of all, let me know what is backtracking. So for backtracking, see here, if it is there are a set of nodes, this is node 1, and there is a path exists from node 1 to node 2, right? And there is one more node 3, and node 3 to this is a 4, and this is 5. If it is so, then the user aim is to travel from 1 to 5. My aim is to travel from 1 to 5. Then I started journey from here, right? Here I have a two paths. I can select this one, and I can have a chance to select this one. So among these two, only one is correct. Then randomly, I don't know which is the correct path. So then randomly assume that you have chosen this path. You have chosen this path. Then what happens that you are moving from this to this, and one station has reached. Then we'll check it out whether this station is 5. Ultimately, we are checking. Always try to reach out for the. Not hearing anything. Is it audible?
Yes, sir, it is audible. Actually, it
Yes,
is a
sir. Okay.
previous message, sir.
Yes. Right. Okay. So now it is we are reaching at station 2. Now we're checking for the always whenever we reach a one station to other station, we're checking for the destination. Whether it is station 5. No, it is not a station 5. Then we try to move ahead, but there is no further moves from station 2. Then what happens that whatever you selected the path from previous node, that is previous node is 1. The selected path is 1 to 2 you are selected. You are assuming that it is wrong. So go back to one step back. Go back one step back. Now, moving back to this one step to the previous station is called a backtracking. Moving back to the one step back to the previous station is backtracking. So again, we are moving from 2 to 1. Then just a minute. So again, just a minute. So now we are moving back to the previous station 1. Again, we are selecting alternative path. So the alternative path is 1 to 3. And once you reach the station 3, again we are checking for whether it is 5. No. So again we are looking forward for the further directions, but there are two alternatives. To select anyone randomly, assuming that is 3 to 4. If it is your move from 3 to 4, once you are reaching station 4, again we're checking for the 5, which is not our destination. Then we are thinking that again we are going to further directions, but there is no further moves from the 4. Then again we are assuming that the selected path from 3 to 4 is wrong. So move back to the previous station 3. So then it is called backtracking. Then again from here to 3, next alternative 5, we are reaching the station 5. So this is called backtracking. All possible ways we can find. Among all the possible ways, one solution is a desired solution. That's what I want to say, that this will be worked out on a brute force approach, where brute force approach will tells us that, or it gives a solution as a one desired solution among the all possible solutions. So here in the dynamic programming, we followed also one solution. Also, we are followed the final solution, where in the dynamic programming. But by dynamic programming for solving optimization problems, whereas backtracking is not for the optimization problems it is used. So these backtracking problems are used when we have multiple solutions. We want all multiple solutions. So, for example, a problem which consists a problem which exists multiple solutions. Then you want to know all those multiple solutions. Then we'll go with the backtracking. Multiple solutions. If user want to know, then only we use backtracking by using brute force approach. Multiple solutions means. Let me draw one. Let's assume that there are three students are there, and there are three chairs. Uh, Three students, you should accommodate three students in a three chairs in such a way that usually there are three factorial ways, right? 3 into 2, 6 factorial. 3 into 2 into 1, 3 factorial ways. We can accommodate three students in a three chairs. For that, we will use one tree structure. So usually what happens that three students in the three stage can accommodate according to the n chairs in n number of students, n factorial, that is 3 factorial. But the solution for this problem can be represented or can be presented in a tree structure. The solution, all these 6 possibilities can be presented in a tree structure. The tree structure is called state space tree. Uh, that is called a state space tree. So I have some. So actually, my device has been changed, so a little bit. The tree structure is called state space tree. Just make a note: state space tree. So, for example, here this boy 1 can be accommodated. So then it is for the next chair boy 2, right? Boy 2 can be accommodated. Next, it is a girl can be accommodated over here. This is one path. You can say G. This is assume that this is G. So such that again one more option that here boy 1 in the first chair, boy 2 in the second chair, right? So in the right side of this one, For example, let me draw one state space tree over here. So here boy 1 can be accommodated. Here boy 2 can be accommodated. And from this, it is a girl can be accommodated over here. Here a girl can be accommodated over here. So this is the one solution. Either after boy 1, next boy 2, here it may be a girl 1 can be accommodated. Such a way there are 6 solutions are there. So there are number of persons. So here if it is again first itself boy 2, either first itself a girl can be accommodated here first itself. Then after boy 2, then we'll go with this is boy 1 and this way girl 1. Or if it is boy 1 here and again here it is girl 1. So such a way there are 6 possibilities are there. Usually there is no condition. What I am saying that here there are 3 chairs and 3 students are there. Among 3 students, 2 boys and 1 girl. We need to accommodate in such a way that all 3 members can sit. So there are 6 possibilities. But I have not insisted, I have not imposed any constraints here, any conditions. But let me check one condition with one condition. The condition I'm telling you that the girl should not be sit in middle of the boys. So the girl should not be sit in the middle of the boys. For example, if you have taken this one, here if it is a first boy, next girl, again if it is boy, then here girl is the middle place. So this condition should not be occur. So then what happens that, so this is a one path, it is a right, this is solution, this is one solution. But according to constraint, this solution is not valid. Why it is not valid? Why it is invalid? Why it is not considered? Because the constraint which is given is not satisfied. The constraint says that no girl is sitting in middle of the 2 bars. Such a way, among the 6 possibilities, and one more possibility also there, then there are that possibility also can be ignored. Whatever the solution will have, a girl will sit in the possibility to sit in the middle of the 2 boys, then those 2 solutions will be deleted from this state space tree. Now, previously, I told you the 6 solutions. Now, there are 2 solutions which are not satisfying the condition. Then final solutions, we will get it only 4 solutions. Why it is 4 solutions? 4 solutions are satisfied according to the given constraint. So this is a total state space tree we can say. But in the brute force techniques, I told you that this backtracking method follows brute force technique. As according to the brute force technique, all possible solutions we need to solve. Among that, only finding possible desired solution with it. So what happens here? All the 6 solutions will make one state space tree. All the 6 solutions. Among the 6 solutions, some solutions may not be satisfied condition. For example, this is a solution we are not considered because of our constraint is not set, such that this is called one brute force approach. And brute force approach is also used for not only for backtracking. One more approach is called branch and bound. That branch and bound is one of the technique for problem solving, which is not included in your syllabus. Just let you know that. So brute force technique is also applicable, also used by the problem solving technique, which is called branch and bound. So in the branch and bound, normally here what happens that I told you that this is a state space tree. In the state space tree, we are following depth first search, DFS. We are followed depth first search. How can you say it is a depth first search? First I have drawn this road, then depth of this, then again depth of this, again depth of this, left, right, and next right, again from the right hand side, left, right, and so on, again right, and so on. This is depth first search, it is following. So just you remember the one word answer, backtracking approach following DFS, depth first search. Whereas I told you brute force approach following the branch and bone. This is B and B technique. Branch and bone technique will follow that breadth first search. Breadth first search. So breadth first search in the state space is like this. First, if it is a boy one can sit, boy two can sit, then girl can sit. So the breadth wise. So breadth wise we are following. Next, if boy one is there, then it is boy two, then it is a girl one. Here, if it is boy two, then it is boy one, then it is a girl. If it is a girl, we will say, and left side is a boy one, and right side it will be a girl. So breadth wise, we are drawing the state space tree. So that's what breadth first see. Search will be followed by branch and bone. Just keep in mind branch and bone. What is branch and bone? That will you no need of that, right? So the main applications of according to your syllabus, the applications of this backtracking. Applications of backtracking is first one is n queen problem. N queen problem. That is queen, king and queen. So here n queen problem is a one application, right? And graph coloring is another application. Graph coloring is another application. Graph coloring, right? And Hamiltonian cycle. Hamiltonian cycle is another application of this one. And also sum of subset problem. These are the four applications according to your syllabus. Sum of subset. Sum of subset problem. Right. So we will go with the maximum cover today. So for example, Enkin problem. So Enkin problem says that for every all these applications, all of four are the problems. In the four problems, we are using a brute force approach in a backtracking method. As you know that backtracking, and we will not predict one desired solution in a single step. Step by step, we are solving. If that step is not achieving your task and your goal is not resolved, if you're following that step, just go back to the previous step and follow the next alternative. And if you follow that next alternative, you may or may not be reached. If it is not reaching, then you go with other alternative. In there is no other alternative, we're not reaching to the particular desired solution, then you can say that it is solution is not there. And but we need to check all the possibilities of the problem. So NPN problem says that there are for let assume that instead of n, let take 4, and then it becomes a 4-pin problem. So consider a chessboard which consists of a 4x4 chessboard, that is 4 rows and 4 columns. So this is a 4 columns and 4 rows and 4. So our aim is to get, there are 4 pins. So we are taking this n value as 4. So that 4 pins we can say capital letters you can write or any one letter. So here Q1 is a 1 pin, Q2 and Q3 and the Q4 are the 4 pins. Let pins are represented with a variable name called as Q1, Q2, Q3. So our aim is to, there are 4x4 chessboard. This is 4x4 chessboard, right? You have to, I told you that we need to arrange we need to accommodate 3 students in a 3 chairs, then we'll get all the possibilities. But once you go with some constraint, then all the possible solutions are not the final solutions. Only some solutions will follow that your constraint. Your constraint is that no girl will be sitting in the middle of the boy. Then two solutions are omitted, remaining four are the conditions satisfied. And before this solving this problem, n-pin problem as a 4-pin problem, our aim is to say first we need to say constraint. The constraints are we need to accommodate 4 pins in a 4x4 chessboard, place 4 pins in this complete chessboard such that constraint 1 such that 2 queens are not in the same row. No 2 pins are in the same row, and no 2 queens are in the same column, and no 2 queens are in the same diagonal. No 2 queens are in the same column. No 2 queens are in the same row. No 2 queens are in the same diagonally same. Such a way you need to accommodate. So, for example, initial one, no. So, and try to accommodate in the first row. You have to fix a position for the queen 1, second row for the queen 2, third row for queen 3, and fourth row for the queen 4. It is not compulsory, but just I am saying that it is better to understand. So here first I will accommodate a q1 at this position. Then I try to place q2 such that the first row should not be used because no two queens are in the same row. So first row we cannot accommodate further next row. And here if this is the position to accommodate q2, then q1 and this one will be in the same column. So it is not possible. If you are going to select this path and these two are the diagonally same, so we'll go with this one. This is the place you can accommodate as second queen, that, and you can accommodate here and check the constraint should be satisfied. No 2 queens, as of now only 2 queens, and q1 q2 not in the same row, not in the same column, not in the same diagonal. So this position is correct. Now try to go for the third queen. Third queen is not possible to place first row, second row, then followed by the third row. It may be possible. No, because no queen is there. But in the first column of third row, it is not possible because q1 comma q2 in the same column. And a second column of third row, it can be possible because third row no queen, second column also no queen. But if you place this is one place for the q3, but q2 comma this q3 will be the diagonally same. So that is also one constraint should not be overcome. So here next we'll go with this one. If this is the position, then two are the q2 comma q3 same column. And if your q3 can be placed here, then q2 comma q3 will be the diagonally same. So all the possibilities in that particular row, it is not possible to accommodate q3. So I told you that if you go with the station 1 to 2, 2 to 3, 3 to 4, and so on, once your destination, once your station, there is no more further routes, and your that current station is not our destination, and further we cannot move, then in that case we have decided that the previous station has selected the route which is wrong, so go back to the one step ahead. So that's why here also you go back to the previous queen. Just we are placing a queen q2 are not correct place. Just change the position of the q2. Go back to the previous step and remove this q2 position. Remove this q2 from here. Remove this q2 from here and try to accommodate somewhere else. So here, if there is a possibility, if it is not possibility, then so that is if what we did here, and here go back to the previous station and we came to here. We came here and again select alternate path, and again here alternative path, go back to here, go back. So until unless that you have to reach a step. And here also same. Here we need to go back to the one step each time, but we can move only one step moving back. So that's what we cannot move directly from the row 3 to row 1. Just go back to the one row back, that is second row we are moving, and try to change if possible. Yes, there is a possibility. We can accommodate here also, no issue, that the satisfied condition that two pins q1 comma q2 is not in the same row, same column and same diagonal. Now try to accommodate q3 over here, then will q1 comma q3 becomes same column. And if you go with this position, you allot q3 here, what happens? Same row no queen, same column no two queens, and same diagonally also no tokens. Then q3 position has been fixed. Fine. Then come to the q4 to place q4. So q4 cannot be placed in the first column of fourth row, and second column of fourth row, and third column of fourth row we can place because no two queens are in the same column. But if you are selected, this is a place, but q3 and q4 becomes the diagonally same. So go with the next position. If the next position is try to accommodate q4 at this place, q2 comma q2 will be in the same column. So all the four positions are there, four alternatives only. Among four alternatives, we cannot accommodate a q4. Then go back one step to the previous, that is third row we have to go. Try to change q3 position. As we have already seen, this is not possible, and that is q3 in third row, third column, third row, fourth column, third row, first column is not possible. And if you place q3, the next queen is not able to accommodate. So this q3 position is not able to change. Then again one more step, go back. One more step, go back. Try to change this q2 position. So if you try to change q2 position, there are two alternates again. It's second row of first column, second row of second column. And in these two places not accommodated, because if you are placing second row first column, q1 and q2 becomes the same column, and second row second column, q1 q2 diagonally will be same. So in this case, now go back one more step ahead, that go back to the one step, q1, try to change q1 position. So change this q1 position from first row of first column to second column. This is the position of q1. This has been moved, right? Now try to decide a position for the q2. For the q2, here it is not possible because diagonal is same, and here it is not possible, same column, because here also diagonal is same. So here we try to place here. So you can say now here try to place q2 here, right? Next, go for the third queen. Third queen can accommodate here the first, try to place for the third row first column. Check out in the first column no two queens, third row no two queens. This has been changed, no? Previously. Diagonal also no problem. So it is a one place for the q3 as of now, no issue, that three conditions satisfied. And now try to accommodate for q4, which is the first row 1, row 4 first column not possible, q3 q1 becomes same column, and fourth row second column is not possible because with the q1 same column. And if this is a position for the q4, row 4 third column, then there is no issue that three conditions are not satisfied. No, with respect to the q3, no other q in the same row, no other queen in the same column, no other queen in the diagonally same. So these are sorry, this is q4. This is q4. So this is the right place. This is a one solution among all the solutions. This is the one solution for the accommodate in the 4x4 board, four queens in such a way that no two queens are in the same row, no two queens are in the same column, no two queens are in the no two queens are in the same diagonally same, right? So this is one solution, but it is not only one unique solution we have. We may have one more solution which satisfying the other three constraints. Let me know if tried anyone. Now here I can say these positions of q1 can be right like this. So q1, where q1 will be placed? Q1 will be placed in the This is a second place, second column we can say. Always assuming that Q1 will be in the first row. So 2 means first row, second column. Q2 will be placed fourth column. That is Q2 means second row. By default, it is fourth column. Q3 means third row, first column. And Q4 means fourth row of third column. This is a one solution set 2, 4, 1, 3 as the places of Q1, Q2, Q3 in a 4x4 chessboard. But it is not unique solution. We have another possibility also. Let me check and please post your answer like 2, 4, 1, 3. If you get another places to accommodate Q1, Q2, Q3, Q4 such that no two pins are in the same column diagonally and row wise, column wise. So try to solve this once again and try to place the Q1, Q2, Q3 in the new position other than 2, 4, 1 and 1, 3. So please do it now. I'm expecting your answer in the chat box. We have other solution. Please do it. So this is the most important. Definitely write NPN problem. Explain NPN problem using backtracking approach. So you can write all possible solutions. I'll wait for 3-4 minutes. Please let me know. Now I'll go with this. Try to find a solution that by placing Q1 over here at third position. I'm waiting. I'm waiting for your answer. At least one. Right or wrong, no issue. Just let me know. Try it. See the solution. If it is third place of the first queen, that is row 1 of third column. then try to place second queen at here. First place, that is second row, first column. Second row, first column. And third queen, here it is not possible, and here it is not possible, and here also not possible. First column, second column, third column of third row is not possible, because here it is the q2 comma this place diagonal, same column, and if you place here, diagonal will be same, and if you place here, that previous q1 and this one in the same column. Now we'll go with this option. Fourth column will replace third queen. So now next q4 position in the first column not possible, as q2 already in the first column, and fourth place is not possible, q3 already there in the fourth column, and here also not possible, but here no issue, as diagonally no other queen is there, and in the same row no other queen, same column no other queen. So then we can say solution is 3. 3 means first queen placed in a third column of row 1. Second queen will placed in the first column of row 2. Third column obviously in third row of fourth position, that is fourth column. And fourth queen can be placed in a second column of fourth row. This is one more solution. This is one more solution. So that's what I can say. Backtracking is so that's what it is. Backtracking is used to solve all the possible solutions. So here we are getting, whereas in the dynamic programming we create an all possible solutions among one is optimal, but here it is not optimal. We have to know all the possible solutions. We use backtracking. So this is also one of the other solutions for the same. 4 queens can be placed in a 4x4 such that 4x4 chessboard such that no 2 queens are in the same row, same column, same diagonally. This is one application of the this is one application of the backtracking. And graph coloring. So the graph coloring, so graph coloring is one of the application of the backtracking. So just I will tell you this introduction. And graph coloring is the one approach for the backtracking approach. Here the graph coloring in general we are using for the mapping in the maps, coloring for the maps. The map may be a state map, a district map, or one country map. So Indian map or whatever it is. So if it is a one region, there is a region called as one state, for example. If it is a one state, can be partitioned again here, number of districts, right? So here, if it is a graph, we need to accommodate. So each district can be shown with a separate color. If this is a one region, this is a one state diagram, or we can say state chart, right? Any other state chart. Here, each one it is represented, each partition is represented a one state. So we need to accommodate, we need to color this graph, color this map actually. So this is map, color this map such that no, the constraint is, so just we can say it is color it. Then if you say, if anybody will say that just color it, So I'll use this yellow for this. For example, I'll made a yellow color with this, and I can also use this with an yellow color. What you told? You told me that just color it. Yes, I'm going to color each state as one color. This is a one color with a one state. So the same color I may use over here. So this color I'll use for over here also. So this is one color I used. So and here I used one color. This is for red color, right? And one more color I used here. This color for this state, right? And one more color I used this green for this color. This is green. Such a way colored it. But what you told that just this is one state chart. So for this you need to color it. But what happens that while taking colors, this is a one. For example, this is one district and this is one district. These two are adjacent. These two are adjacent, and I used the same color. But you are not saying that any constraint. Just you color it. So that's what this is fine. This is for good. This is a right answer. But if you are saying that the constraint is that color a given chart such that no two adjacent district will have a same color, because you see, you select any chart, India map, world map, whatever it is, no adjacent state or country will have a same color. Color will be same for a country to two countries will have the same color, but those two countries are not side by side. See your any chart. So here what happens that in this chart, these two districts will have a side by side, and you use the same color. So this somewhat difficult to segregate. This is one district, this is one district. To make sure that there is easy for segregation, the constraint it is that color a graph or a map such that no two adjacent districts or states or countries should have the same color. Then what happens that here you have selected no the previously, that is wrong. Then we go with should not have a yellow here, some other color. And make sure that whenever you use this color for this state, and check out the colors for the adjacent. Adjacent is this one, and this one. There are three states are three districts are adjacent, which are one is yellow, one is violet, and one is green. So now I'm using for the pink for this purpose, no issue. So then we can say that this is graph coloring. Graph coloring approach we are following that graph coloring is used to color the graph in such a way that the constraint is that no two adjacent nodes. So here I am using graph. So graph can be converted into, or else you can say this is one graph. Yeah, this is one graph. So color this graph. Two adjacent color nodes should not have, constraint is two adjacent nodes. If you want to color this, you initially use this any color. So make use a black. So now we'll go with the for coloring of this node. This node should not be black because this adjacent node will have already black. So I used some other color, this one. And next, for the next one, this I should make a color which is should not have a black, which is adjacent one. This and these two are adjacent, and this also two adjacent, but which is not at all colored, which is not yet colored now. So now we'll go with right to make this color should not be pink, should not be green. Use any other color, and I used over here. Right. So tell me how many colors are used for this graph. Anyone in the chat box? How many colors are used? I used how many colors to color this graph? I used four colors. I used four colors: color black, pink, green, and yellow. Four colors it is used. I can. Is it possible to color these nodes, four nodes, with less than these four colors? Less than these four colors. Can I use less than these four colors? So here for this, assume that this black is only. Otherwise, I'll draw one. So this is the mode. Yeah. So same thing, which is black already used here. See, assume that this is color one already used, right? And can I use the same black color for any other remaining nodes which are not adjacent to this? So can I use black for this? No, because these two are adjacent. Can I use black for this? No. Can I use the same color for black? This? Yes, you can use. Yes, you can use a black over here, which are these two are not an adjacent. Adjacent means not connected with each other directly. And next, these two not possible to use black. No, then I'll go with some other color. So I'll make one color for this other than this black. And let me check here. This should be connected with, for example, node one, node two. This is node three, and this is node four. So 2 is adjacent to 1 comma 3, which are black colors, and here it is used pink, no issue. Constraint satisfied. Two adjacent nodes should not be same color. Yes. And 4, which color can I use? I can use other than black. 4 is adjacent to 1 comma 3, which are already used for 1 comma 3 as black. So don't use black, you can use any color. So I can go with a new color, or I can use the same color which are used for the node 2. Same color you can use, no issue. So what happens if they use same color? The number of colors used to make this graph is now it is two only. Now it is two only. Otherwise, some people may select for the fourth node, you may go with the blue also, no issue. You might some other color. In this case, total number of colors used is pink, black, and blue. Total number of three colors. So there is a possibility of using coloring the graph for four colors, for three colors also possible, for two colors also possible, and with a minimum of two only, not less than two. It is not possible. That is, with one color we cannot color all these nodes. So there are three possible solutions to color this graph. This is the backtracking. So that is all the possible solutions we are finding in a brute force approach. So all possibilities, possible one is four colors, possibility two is three colors, possibility is two colors. So among these, desired solution, always desired solution should be cost factor. With respect to the cost factor, I should try to use minimum colors. If it is minimum colors factor is your constraint is that try to use minimum colors, then you'll go with this two colors graph. No issue. Any number of colors are used, then they'll go with the three color graph or four colors graph. No issue. There is no constraint. The number of colors is not mandatory. There is no constraint in the number of colors. Then it is okay. If the constraint is that try to use minimum number of colors, then I'll go with the two color the graph. With the two colors only, I can have a possibility to color the graph. So this is about all theory part. Then we'll go with one problem also over here. And based on this only, we'll write an algorithm for this graph coloring. And also that here I discussed, forgot to say, here I discussed here 4 queen problem, but it is not always 4, n is equals to 4. It may be 8, it may be 16. So if it is 8 queen problem, so you have to arrange in such a way that there is an 8 by 8 chessboard instead of 4 by 4. Now it is 8 by 8. So 8 by 8 chessboard, you have to draw 8 by 8, 8 rows and 8 columns such that 8 queens should be placed in this board, such that no two queens are in the same diagonal, same column, same row. So it may be 8. Sometimes in the question it may be asking 8 also. Sometimes it may be 8 pin also. Right? Uh, then it is a graph coloring is one approach for graph coloring. This is the one more technique. Then Hamiltonian cycle, sum of subset problem, we will see in the next session. So is it clear? So, so the previous device is locked. That's what little bit we are strained over to constrain to draw this. And next class I'll get it that device, but today only just little not so good this one. From your side, students, let me know anything about this backtracking. I'm waiting to see reply in your chat box. Okay, then you can leave. Now we'll stop this today because it is not so comfortable this device. So we'll see two more applications, Hamiltonian cycle and the sum of subset problem in the next session. So today I will stop this with these two applications only. You people can leave.